Yeah. So good morning, everyone. Quick introduction about myself. I'm Vijender. I'm the founder of Almix AI Labs, a firm I started a couple of years ago, and I have about 20 years of experience in tech industry. And I have worked as in almost every role that is there in the tech space. Okay, from being a developer to everything. I have an MBA too. So, that's why I've done product management, account management, strategy consulting, all sorts of stuff, right? And my last stint was as the director of engineering and data science at HighRadius, right? Prior to starting this. And yeah, so at LMSA Labs, again, quickly, we do build a couple of products. One is AgriGPT for Indian farmers, and the other one is an innovative product we built for EdTech called Study Buddy. Okay, so but again, I won't bore you into all that. Probably we'll get deeper into what we're trying to do today. Okay, so today's session is about fine tuning. Okay, and I thought it'll be interesting because I myself have been trying to read a lot about this for the past few months now. Okay, and I'll tell you why I'm conducting this session also. And every time you go and check out some of these YouTube videos, right, there will be these long videos which will look like they're teaching you a lot of stuff. But ultimately, when you actually start diving deep, you will be like, does this guy have a clue about what this guy is saying? Correct. So more often than not, it's just a long video which you feel you have read through, but nothing sinks in, right? And then we let it go, right? And we let it go, and I've also let it go for a very long time. And so one fine day, I said, nothing doing. Let's get to the bottom of this. Okay. We have a NVIDIA 810G GPU. And I said, chuck it. Whatever happens will happen. Let's do it. Okay. So I run a training cohort as well for people who are upskilling in AI. I do it for corporates. So I'm doing for a company called Inspire currently. And I also do it for working professionals who need, upskilling. Correct. So want to get into AI. So we have a small cohort of people, and I'll share shortly. In fact, let me just see. So there is an application which we built also for this. Okay, where is this URL? So I'll show you there what we built, and yeah. So our core members have actually built a UI so that you can actually see what is the output of this fine-tuned stuff. Okay, so that it's just not some boring, just another video which is showing you PPTs. Okay, so no PPT business. I'll show you directly in Eraser. We'll talk about stuff. I'll teach from the basics in terms of some basic concepts of neural networks as well. And then we will actually see in an NVIDIA GPU, and you should feel that excitement about how it works. Okay, that's the missing link I feel about the other YouTube stuff. Okay, so before we start, any quick questions in terms of what are we doing, how are we doing, and all? Any quick questions before we start? Okay, all good. Okay, great.
I wanted to ask, hi Vijender, sorry to cut you in, but I wanted to ask, like, do you think that we need some specific specialization, as in some background in engineering, some sort of? Because I'm a mechanical engineer and done masters from IIT Guwahati.
Okay.
And currently, but I'm working in a domain where I've worked with lots of data, and I've done like ML development. And I regularly use AI chatbots and all, and RAG implementations and all. So do you have any idea, like, do you need some basic requirement before we start the session?
Correct. Yes, we do. Again, it depends, Himanshu, right? Like, you definitely need maths, right? If you want to get deeper into all this, you need maths, you need to know vectors, you need to know matrix multiplications, and you need to be good at Python, right? That's these are the prerequisites, right? Maths, again, it depends. You need to know calculus, you need to know derivatives, loss functions, gradient descent, and all that do require. Now, again, it depends on what is your ambition, right? Do you want to be at the application layer, or do you want to be at the model development layer, correct? So if you really want to get into the model and play around with it, tinker around, you need all that advanced math. But if you are more the application layer, calling APIs and stuff like that, then I don't think you really need to get so deep, correct? But with respect to what we are doing, again, with respect to fine tuning, what I will show you today is we take a pre-trained model and we fine tune it, correct? So fine tuning is, again, it looks simple. It's just a script, we run it, and it looks simple, but there is a lot of engineering behind it in terms of all the parameters you send, how many epochs do you give, what is the learning rate. All that is a lot of engineering decisions, right? And that's where the value is in terms of AI engineers or people like us who are into, that's why people hire such people, right? So should I put an epoch or 10 epochs, 20 epochs? What is it? What is the learning rate I need to give? How does it impact, correct? And how does it impact the quality of the model? Should I go for LoRA, QLoRA? What should I use? What are the resources I have? So that is the main thing about all of that. So I think, Himanshu, if you once we complete this session today, you'll get a fair idea of what to expect. Okay, so then we can connect offline, right? Let's do that.
Sure. Thank you.
Yeah, thank you. Fine-tuning LLMs. I think Parthasadi has a question. Covered traditional ML probably doesn't need GPU. Yeah, you are right. Today we're doing fine-tuning on LLMs, right? So if you try to do traditional, ML, right, it's not going to work. Okay. If you try CPU, I'm sorry, my bad. So if you're trying to do this fine-tuning on a CPU, it is not going to work. Okay, you can't even run a model also. So that's why putting it on a GPU helps. And we also have GPU from Collab, right? Collab provides. I'll show you that also. And then I'll tell you what the difference is with respect to the NVIDIA i10G, which I'm going to show from my server. Okay. So let's get started. Give me a second. So I'm trying to get that. URL. Okay, guys, so let's get started. So first thing is, before we even start, all the, fine tuning and all, it's important to understand the basics of models and parameters, right? So all of you might have heard about parameters, right? Llama 40 billion has 40 billion parameters. Gemma has 3 billion parameters. I think GPT-5 has GPT-3 had around 175 billion, and I think GPT-5 now has some trillion parameters or something, correct? So anybody wants to take a quick stab at it? What are parameters? And you see here parameters, weights, and biases and all that, right? Does somebody want to take a stab at it? Any idea? What are weights and parameters when you talk about these models, right? Anybody wants to take a stab at it? All of you are new. Anyone already ever tinkered with this? No? Okay, good. So what I'll do is I'll share some quick overview of what are weights, what are parameters, and what are biases, and what's the relationship between them, so that is the basis for fine tuning. Because without understanding that, you will not understand how this whole fine tuning is happening and what is the benefit of one kind of fine tuning process over the other. Correct? So let's start out with a traditional, typical neural network. Correct? So if you look at a traditional typical neural network, I'm sharing my screen. Yeah, you can see my screen, right? Yeah. So I hope I'm audible, right? Audible and screen is visible. Just thumbs up, please. Quick. Yeah, thumbs up. Screen is visible. Yeah, great. So this is a traditional neural network kind of, what you typically see, every time somebody talks about neural networks, right? You have an input layer which has n nodes. You have neurons, right? H1, H2, so on up to Hn. So here we have 3 hidden layers, but you can have H1 to Hn, right? N hidden layers. And then you have the output layer, correct? So these input layers are what goes into the model, correct? And the output layer is what is coming out of the model, correct? So within that, these hidden layers, H1, H2, H3, are the hidden layers you have for various purposes. So each layer helps to take the inputs and convert it into a format that will help you get a meaningful output, right? Now, typically, again, if you look at all of what is the terminology? Terminology is H1, H2, H3 are the hidden layers. You have these circles are all neurons, correct? And each line on these, correct? Each line on these represents a weight, correct? The weight from this input to each of these n nodes, right? Second input to the n nodes, third input to the n nodes, correct? So when you say input, what is it? This is a cat, let's say, right? Or how are you doing? Or tell me the capital of India, correct? So when you ask a question like that, typically that is what gets into the system, correct? And can someone tell me what happens, when you say what is the capital of India, right? And you get New Delhi. Can you tell me what happens under the hood? Where does New Delhi come from? Anyone? Can someone tell me when you say what is the capital of India and you happily get the response New Delhi, right? So can someone tell me how does that New Delhi come? Is it like stored in the model, in the brain somewhere, or is this coming from a database? Any idea?
Like, as much as I know that whatever keywords we have actually entered, so it tries to actually make connections. Like within the hidden layer, it will try to identify where these actually words appear, and then it will try to make these internal connections which it has learned, and then in the end, whatever is the most suitable answer, it will come up with that. That is my understanding.
Correct. It does come up with the most suitable answer, but where is the New Delhi coming from exactly? Like, is that within the model, or it's coming from a database, outside the model? Any rough thought there?
I think it's been trained on that database, so that's why it's where it's extracting the data.
No, it's not from a database. Okay. Anybody else want to take a stab at it?
It comes from the tokens, like output will be the token corresponding to the New Delhi.
Correct. That's right. It comes from tokens. Correct. So what happens is all this input text that will become. No? Who's it? So basically, whatever is the input we are giving, right, it all gets converted into tokens. Yeah. So these tokens are passed to the, these tokens are converted into embeddings and sent inside, and all these layers they pulled out. So I'll just show something here. Okay, quick understanding purpose. Okay, so you can see my screen, right? So here, if you see, the input layer is all this x1, x2, x3, so on, right? These inputs are x1, x2, x3, and that's the input layer on the left. Then you have the hidden layers in the middle, right? So these layers perform the actual learning by transforming inputs into increasingly abstract representations, and then you have the output layer, correct? So H1, H2, H3 are the hidden layers that we've already seen, okay? Now, if you see what happens inside each hidden layer, right? I told you H1, H2 up to Hn is there. What happens is each neuron, right? What is a neuron? Each of that is a bubble, correct? So the bubble, what it's saying is it will do a computation, okay? It computes the sigma of W1, X1, where W1 is the weight corresponding to each edge that connects to the input to the corresponding neuron, right? So you have the input 1 here, it connects to this neuron, it has a weight. The input 1 connects to this neuron, it has another weight, correct? So typically, if you see in a neural network, right, if you're saying you have weights and biases, what are weights? Weights are nothing but the second. Yeah. So weights are nothing but what are connecting the inputs to the neurons, each one of these neurons. Okay. So if you are seeing here, we are computing the W1 X1 plus W2 X2 plus so on plus a bias. Okay. So bias is a single value for each neuron. Okay. So if you see over here, input 1 is connected to how many neurons? Let's say we don't have these 3 dots. Let's say we have 3 plus 6 plus 1, 7 neurons. Okay. So input 1 is connected to 7 neurons, input 2 is 7 neurons, and input 3 is 7 neurons. So how many weights are going to be there? 3 sevens are 21, right? It's just a multiplication, right? So again, 7 neurons in this layer multiplied by 7 neurons in the next layer. That is how many? 49, correct? So it's the total number of weights in a system is a function of how many neurons are there in each layer multiplied by the weights. But the bias is only 1 per neuron. Okay, so that's why if you see, let's say you have 10 neurons here and 10 neurons here, you have 100 of them, you will have only 20 biases and 100 weights, correct? So if you increase the size of the neurons, the count of the neurons, you will soon realize that if I have 100 neurons and 100 neurons in another layer, it's 100 into 100 is 10,000. But the total number of biases would just be 200, correct? Because it's 100 plus 100, right? So that's why if you look at it in terms of the total number of weights and biases. So what is parameters? The definition of parameters is the sum of the total number of weights and biases. Okay. So here, if you see the count, whenever we say it has 40 billion parameters, it is nothing but the sum of total number of weights and biases. Now you'll notice that if I have 100 neurons into 100 neurons, that's 10,000 versus 200 is, you see the biases is very negligible, right? So that's why you see people saying, 650 million parameters or 650 million weights. Pretty much they say it interchangeably, correct? So parameters are like the numbers inside the model that store what the model has learned, right? So think of parameters as the brain cells of the model, okay? So imagine if your student is learning English to Telugu translation, it's vocabulary learned, grammar rules, and sentence structure, right? So all of this knowledge is stored as numbers, and these numbers are parameters, okay? So mBart50 is a model which we are going to fine tune today, and it has 650 million parameters, okay? It is a pre-trained language translation model from Facebook, okay? And it has been trained on 50 languages, and this is what it is. Now, what are weights, right? So weights decide how important something is, correct? So let's say you're just listening to music. So what is more important when you're listening to music? The voice volume has more weight as compared to the background noise, correct? So weights decide what to focus on more. So let's say I eat rice, right? So if I'm saying I eat rice and I want to understand what are you eating, then what is more important in that context? So rice is more important when I want to understand what you're eating, okay? So biases are that extra small number added to help decisions, correct? So let's say I have, again, it's like that extra push within each layer, right? So if you see the output, right? So input into weight plus bias, that's what is that x1 w1 plus so on up to xn wn plus bias is, correct? So each cell, if you see here, each neuron computes this function, which the summation, right? And you pass it through an activation function, right? And the activation function can either be ReLU or sigmoid or tanh, depending on what you want to choose. And the output of that neuron, that value that you get, that A, is the output that you get from the first neuron, okay? And then the same output you get from the second neuron, and that's what gets passed on to the next layer and so on and so forth, right? So typically at a high level, again, you don't have to get bogged down about each one of these, but this is what happens at a high level, okay? Now, again, I'll skip a few of these because now I'll talk a little bit about how does that, how do we predict the, so this is at a high level, this is what happens, right? You have X inputs, and then you get into a summation function, then the activation function, and you get the prediction, right? And you have a bias added to it, correct? And that's how you do the predictions at each neurons in each layer. It moves on and it improves it. So why do you need so many layers? Because each layer does some piece of work, right? Some piece of enhancement, right? I think there's one slide there. Yeah. Okay. Now let's look at how do you answer the question, right? What's the capital of India, right? Now, how does weights and parameters help to answer this question called what is the capital of India? And you get a target answer as New Delhi, right? So it's magical, but a lot of people think that there is a database inside or it's stored inside somewhere, and it kind of predicts the next word, but still gets it as a text. So that's not true. It predicts it as tokens, and it uses vocabulary to get the result back, okay? So the first thing is the model does not store lookup facts like Google, okay? So the thing about this is it does not look up facts like Google. If you are saying what is the capital of India, the first step, right? There are several steps that happen. The first step is it breaks down into tokens, right? So you see what is the capital of India, correct? So how do you identify what tokens are there? So typically, if you want to look at it in OpenAI, they have the tokenizer, OpenAI tokenizer, right? So OpenAI gives you this, okay, tool, which all of you can use. So I just put it on the message here. So in this one, if you see, right, you can actually type what is the capital of India, okay? And you can that it capitalize tokens, right, on the basis of this. And the token IDs it gives for each one of them are these. So these are the token IDs, which is the first step for any LLM, right? They have to do this because without this, they don't understand English. They understand tokens. So how are these tokens generated? Basically through vocab, right? So whenever they go through petabytes of data, they convert them into tokens and convert them into vocabulary. Those vocabulary, each word, right? If you see what is capital has a token ID, right? So if you see here, if you want to understand what is that token here, you can just say yes, capital. Okay, this is the token corresponding to capital. So word to ID number. pretty much. Okay. Now, if I just ask something interesting. So this guy is just asking for an MFA. Just give me a minute, please. So we just connected the inference of this onto the front end. Hey, just pass this to the. So it's just asking me for the MFA. Just give me a minute, please. Okay. So what happens is these tokens, and again, when they get into the system, and okay, let's get back to our PPT. Yeah. So what happens in the capital of India is it gets in, and each one of them becomes a token, correct? And these tokens convert to embedding parameters. And then if you see, attention starts kicking in, right? The next thing is attention, right? So, okay, I'm sorry. I have a question for you guys, okay? So those who know what these tokens are, right? Pretty much. So if you say, what is, Bob is playing in the part, okay? So what is the token corresponding to playing? If you see, right? You can see the text over here. Bob is playing in the park. You can see that the third token corresponds to playing, correct? So you can see that it's 8252, correct? 8252 is the token, correct? But if I say playing is fun, okay, what is the token corresponding to playing now? If I see the token IDs, it's 41323, correct? Can someone answer why this is happening? If anybody is aware of how these tokens work, how the tokenization happens. So there are various algorithms, right, like byte pair encoding and all, which do this tokenization. But just a trick question, if anybody is up for it. Does anybody know tokenization?
So Vijender, is it because the meaning of playing is different in both the sentences?
No, this tokenization has got nothing to do with attention, right? Tokenization is pure play, vocabulary, word to ID. That's it, right? I take a word, I have an ID. For example, here, if I'm seeing here, right, playing is fun. You can see that how it's kind of splitting, right? Playing is fun, 3 different tokens, and it's what it is, correct? Now, if I'm saying Bob is playing in the park, right? You'll see that again, you're splitting it up. These are how the tokens are created, right? And they get their IDs from the vocabulary. So if you say Bob has its own, his or her own token, right? But the question I'm asking you guys is, playing seems to be having a different token here, right? As compared to the other one. So if you see the token corresponding to this, playing is 8252, correct? The third one, right? But if I say playing is fun, it seems to be having a different token, right? So 41323. So I'll tell the answer. It's not easy for for a long time I also didn't know the answer. Huh?
It's related to context.
No, it's not context. A lot of people think that. So there's no context here. It's pure splitting
Like
of words.
according to the before and after.
No, you're saying attention on all that?
Let's say playing is the fun.
Yeah.
Playing coming in the front.
No, it does got nothing to do with playing is fun. If you look at closely, right? When you say Bob is playing in the park, okay, just observe this, okay? Because for a long time, I know my theory, right? I was very clear that token ID should never change for a given word, right? That's the theory. And I was like, OpenAI cannot make a mistake. So then when I looked at it in close, if you look at it in detail, it's space playing, right? The token is not playing, the token is space playing, right? But if I look at it as playing is fun, okay, you'll see that the token is just playing. So you have a different token ID for space playing, and you have a different token ID for just playing, correct? So that's how it differs, right? And that's the thing behind it, right? Now, again, you might be wondering why is space playing a different token as compared to playing by self, correct? Maybe that's a way of OpenAI trying to say, if I have space playing, it means that it is following something, correct? Whereas if I have just playing, that means it is starting with that sentence, right? Pretty much. That's how that's how they build the algorithm, right? So this entire tokenization algorithm is again individual to different LLMs. They have their own algorithms, and I think most of them use byte pair encoding, correct? Now, any questions so far? All good, right? So again, I have a question for you guys. What if somebody says space playing is fun, right? Then it's going to take up this token and it can give a different output, right? What do you guys think? Now, if you see this 59742 is given the same thing now. Okay, got it? So it's given the same as the one before. So typically what I think they will do is they'll just truncate the leading spaces, correct? And then they will do the inference, right? But anyway, let's not get deeper into it. That's a big science by itself. We can build our own tokenizer, guys. Okay, so people in my cohort have built their own tokenizers also. And yeah, so let's move on to the next one. So what is the capital of India? Let's go back to the original one. Now you have some context, right? So when I say what's the capital of India, is broken down into tokens, and then you come into embeddings, and then you're having capital and India, right? So the attention weights become high. So now in step 2, you're checking the attention, right? So basically, the entire architecture of GPT revolves around the paper from Google it's called Attention is All You Need. In 2017, Google launched it, correct? And then OpenAI took that and modified it for the transformer architecture, right? So here, if you see, the attention weights say capital and India are high, right? And the other ones, like what is the off, they are low, correct? So what is the visual focus that the model lays attention to? Capital and India, right? This is strong attention, right? So if you see, during training, the model saw millions of sentences like this. The capital of India is New Delhi. India's capital, the New Delhi is the capital of city and all, right? So every time it started training, it knew or it understands that capital plus India, whenever they occur, New Delhi is the best option. And why is it the best option? Because it calculates the probabilities, correct? So it calculates the probability of the next token, right? So ChatGPT works on the principle of predicting the next token, right? So if New Delhi and capital of India comes, the probability is high. Mumbai and the capital of India comes low. India and the capital of India comes very low. So what is the best probability here? New Delhi for the capital of India. So that's how it does the next token prediction. And again, it does not predict New Delhi. Okay, it predicts the token corresponding to New Delhi, and it reverse maps the token ID to the vocabulary to determine New Delhi. So ultimately, New Delhi resides in a text file somewhere, right? But what the model predicts is not text. What model predicts is the token ID. Cool. So, but again, these probabilities, where do they come from? They come from matrix multiplication using weights again, and that's why you need GPUs, because thousands of computations are done in parallel. Okay. So that's why this is what it is. And so training, basically, again, if you look at it, why am I talking about all this? This is the foundation for understanding what are weights and biases. What's, how do the parameters play a key role, right? Now, fine tuning, basically, typically, if you look at any pre-trained model, like you have pre-trained model versus fine tuning. So mBart50, 650 million parameters is a pre-trained model from Facebook, where they have spent a lot of GPUs on training 50 languages and given it to us. But we want to do English to Telugu translation, and we will see that the output is not great if you use a pre-trained model. So we want to improve it by fine-tuning with some data set coming from Hugging Face. Okay, so we'll actually do it. I'll actually show it. You'll actually see what's the difference. Okay, so that's what we're talking about in this session. Okay, and the goal is not to just talk theory. It's about seeing it in and to believing it. Okay, so that's, I think, something that you don't find anywhere, at least to my knowledge, right? Most of them just open PPTs and then just they bore you to death, right? Next thing is, okay, so I give Vishal's contact to Vamsi. Vishal Pun's contact to Vamsi. So the next thing is, okay, let's now look at, again, typically, again, why do we need to do fine tuning? Okay, I'll just talk about it. I mean, I don't want to deviate too much, but I'll just still talk about it. So typically, if you see an LLM has a knowledge cutoff, right? And someone tell me, what is the knowledge cutoff for ChatGPT? You understand what knowledge cutoff is, right? So the last date when the model has context of the world, right? The last deployed model. Can someone tell me what is the knowledge cutoff for OpenAI? Yeah, latest to 5.1 or 5.2. What is the knowledge cutoff? I mean, you can use ChatGPT. You can use ChatGPT. What is the knowledge cutoff? Anyone? Yeah, August 31,
August
right?
24.
August 31 of which year?
2025.
That's correct. That's correct. Yeah. So it's basically August 31st, 2025. So which means that after that, he doesn't have any clue of what's happening in the world. Correct. But still, if you ask a question after August 2025, it still gets the data. How does it get it?
They have a tool.
Tool.
What tool? Yeah, no, they don't use RAG. I think they don't use RAG. What? Huh?
Web tool.
Web tool. Yeah, they search. You say searching, right? You see searching. So internally they call some search API or something. I don't know what they call it myself. I don't know. Yeah, they use some search tool at the end. Correct. So that gets the data out. Correct. Now the point is, if I mean that's what OpenAI can do, but if we are using an LLM, right? How do we enhance its knowledge? Correct. So there are two ways of how you can enhance the knowledge. One is by RAG, okay, retrieval augmented generation, and the other one is fine tuning it. Okay. So RAG as such is you keep the original model as it is and just augment it directly. It's simpler, but it has its own challenges. Fine tuning is much more better to get better accuracy, but it's a lot more complex. Correct. You have to train and deploy it, manage it, and all that stuff. So that I'll just leave it over there. I don't want to get in deep depth of RAG and pros and cons and all. So what are we doing today? So we are basically taking this mBart50 model. Okay. So I'll put this link also. 1 second. Yeah. So I'm putting it in the link over here. You folks can access this. Okay. Okay. Just open this. So all of you can open this meeting link, right? So this is the English to Telugu translation, which we are trying to run on in our NVIDIA 810G, correct? So this is from Google Colab. So if you run a Google Colab, it gives you a TPU, a GPU, correct? Can someone tell me what is that configuration? What is the configuration of GPU that Colab gives you? T4, correct. Is it T4 or T2? T4, correct, you're right. So it gives the T4 at the top right, correct? So typically, if you run the first cell, right, it starts connecting to the T4 GPU, and it will start executing this, okay? So now if you look at the code over here, pretty much, right? So I'll just walk through the code. So before we go forward, anybody, any quick questions? Any quick questions? What's going on? Anything so far? All okay? Yeah? Question, okay. Patsa, there's a question. Yes, please go ahead.
Hi. Vijay, this model right from Facebook, is it for many of the Indian languages, or for example, will it work with the Tamil, Sanskrit? Because I'm more interested in Sanskrit. Maybe I can talk offline many things philosophically, right? Yeah, let's just. Yeah.
You can check it out. You can check it out yourself. It's coming from Hugging Face. It's not my model. Okay. So you can actually search for mBart50 and you can search it by yourself. I'm putting the link here anyways. Okay. And it's actually trained on Telugu as well. Correct. So if you see and use this model out of the box, it will actually give you inference out of the box as well. Correct. So we actually developed these endpoints. I hope we are working. Let's see. Yeah, it looks like. Yeah, so we'll actually, actually you can see them working, right? So we have 4 versions of it. I'll come to that, okay? So to answer your question, you can check it out yourself. What are languages? There are 50 languages, you can check all of them, okay? So yeah, these are the languages, okay? People answer, right? So do we have Sanskrit? Let's see. No, I don't think so. So Telugu? Yeah, you have Telugu, right? So Sanskrit, no. Yeah, I think it has Hindi also. Yeah, it has Hindi too. Okay, cool.
Yeah, I don't know why it's very, sorry, Vijay. I don't know. See, it's all came from Sanskrit, right? Hindi, everything, the base, right? These are like typical thing. I don't know why Microsoft, Google, Sundar Pichai, all are Indian guys sitting out there, not giving priority. I don't know. This is just a thought. Maybe Indians are developing something from IIT on specifically on this.
So
yeah, sorry, you got my point, right? Yeah.
No, I got your point. So again,
natively it looks
right?
like natively it is not supported, right? Natively it looks like it is not supported then.
Yeah, it's not pre-trained. That's how it is. But the point is, some of this requires data, right? Ultimately, to pre-train these models, you need data. Now, maybe they don't have data, and that's where the knowledge of this is important, and to understand how you can do it yourself and contribute. Why not, right? See, today, if you look at it, ChatGPT, Gemini, Claude, Grok, all of these are based out of US, right? So one fine day they say, hey, I'm not giving access to Indians to any of these models. We are all stuck, right? All our AI applications just stuck not working, not one of them will work, correct? I know they won't do that for commercial reasons, but that's the kind of dependency we have today. So why not understand from the bottom up and build it ourselves? Why not? We can, very much we can, right? So in fact, I done a program, cohort program, where we are building an LLM from scratch, right? So and some of our guys who are just junior folks, they are also participating. So that's how they know the tokenization and all that, right? So we built our own tokenizer, and we are starting from there, building embeddings next to using tensors and all that. So short answer to your concern, valid concern, but I think it's better we try it and find a solution ourselves, and we will get data for this. Okay, we'll definitely get data for this Sanskrit, and we should be able to build it. Okay. Now coming back to the workbook. Okay, so the first one, we are just installing the standard dependencies that we need from Python, right? So transformers, data sets, pandas, torch, and all this stuff, correct? And again, from Hugging Face, we need whatever we need, and then we are importing the libraries from these dependencies, and then we check the NVIDIA -SMI. Okay, so just keep running these cells one after the other. All of you can do it in parallel. Okay, so it's a code along session, if you may. So just run it. It'll be sweet. You don't have to do anything. No mental effort. Okay, just clicking buttons. But understand what's going on. It says importing from transformers. It's importing whatever it needs, right? So sequence to sequence, trainers and all we are pulling in. And yeah, please come. So this also ran. Next is you run NVIDIA SMI. If you're able to get an output here, it means that your GPU is running, right? Or otherwise you're on a CPU. So if your NVIDIA SMI doesn't work, that means, of course, it's not an NVIDIA GPU, right? So that's when it gives the output, means it's working, correct? Now the point is, does anybody know what does Google use? Google has its own. Does Google use NVIDIA GPUs? Anyone? Yeah, it uses GPUs.
They have their own tensor chips, right?
Yeah, they have their own tensor chips. Yeah, they are called tensor processing units, right? Is that what it is, Atman? TPUs. So Google built its own architecture. They said, I don't want to depend on NVIDIA. Let me build my own stuff. And they are the only people who have their own stuff, correct? But the question I have for you is, this is the GPU, right? So can anyone answer, if Google has TPUs, why are they exposing a GPU to you? This is an NVIDIA GPU. You can see it, right? NVIDIA CUDA version is installed. It's an NVIDIA GPU. So why do you think they are exposing to us GPUs rather than TPUs? Ever wondered why? Because if it's their own infrastructure, it makes more sense, right?
Maybe the other models are made for GPUs, other models that we want to run.
So again, your models, it will not be a function of the models, correct? Typically, it's not a function of the models. I read the reason. I think I almost forgot about it. I think it's got to do with the fact that running this kind of computations, what we are trying to do in terms of fine tuning, is easier on a torch powered platform which runs on CUDA on a GPU, right? TPUs, Google has its own way of working with its TPUs, correct? It's proprietary, it's custom, and it's not easy to expose it to people like us on a TPU, right? So they use it for the internal stuff, but they cannot expose it like that. So that's why they're still like giving you GPU access.
It's like framework specific, right? Vijayendra, if I'm not mistaken, TensorFlow would work better with a TPU than a GPU, I assume, right? Because TensorFlow is from Google.
Yes, something like that. Something like that. Yes. Your torch. See, ultimately, you need to run torch, right? Over here, you need to run torch, and you'll see it when I show the GPU how heavy torch is. Now here, if you see, I just ran this play button and it ran in 9 seconds, and it ran, right? Does anybody have any idea how much of size this particular virtual environment creates? When you install when you run any Python project, you will create a virtual environment, right? Nowadays, it's the norm. So when you create that VENV, what is the typical size of that folder? Anyone? Again, what is the typical size of any VENV folder? Anyone? When you do Python projects, typically average. Anyone has worked on Python development for any projects? I know RAG. I think Himanshu, you worked on RAG, right? You would have used VENV, right?
Yeah, I mean,
have you checked the size
virtual
of
environment when we create for the first time, so that size will be smaller. But as you go on and install the different libraries, then it keeps on increasing. So it varies actually.
Correct. Yeah, it varies. You're right. So initially, but approximately, right, for typical project use cases, unless you're using Torch, it'll be like 60 to 80 MB, correct?
Mhm.
With all your, typical packages what you install.
If you install the TensorFlow, then it will be like in GBs as well. TensorFlow
It will be
plus its
several GBs.
dependent
So,
libraries. Yeah.
so we don't use TensorFlow, we use Torch. Okay, so TensorFlow is kind of old as far as people say. Some people say it's also dead, but I don't know. But pretty much PyTorch is what is in vogue now. Okay, so if you see, I'll show you on the GPU what is the size of that folder which comes after you do the entire pip install and all. But now here, if you see, because of the collab environment, you don't realize the pain because it just does it for you. Correct? Everything is taken care of because it already has it in it. So if I'm not mistaken, these guys already reuse some of that. They don't do that installation like what we do on our systems. Okay, that's why it's fast. You've seen it has taken 9 seconds, but the GPU, it takes a hell of a lot of time because it's huge, right? Several GBs. Now you import all the libraries and you ran NVIDIA SMI, and then you're preparing the data set. Now again, typical fine tuning process, right? What is the process? You kind of download your data set for which you want to fine tune, correct? Ultimately, it's all about you're taking a base model, which is mBart50. So you can see that this is the base model we are taking. Where did that go? So this is still the data. Yeah, this is the base model from Facebook. Okay, if you see Facebook mBart large, this is the model which we are picking. And what we are trying to do is we are fine tuning it with our own data set. So where is this data set? This is the data set. Okay, data sets Shreya 3095 Telugu data set, right? So we can actually open this. Okay, you can actually, all of you also can try for this. Okay, so you'll see that it's over here, Shreya 3095. And you'll see that, where is the data set in this? Data set card. Yeah, so you can see the data is here. Can you see this? This is the English to Telugu. So this is the data set which we are training our fine-tuning our model on. Okay, that's what it means. Sounds good? So we're taking official information and Adhika Saramacharam, like, of course, I'm sorry if some of you don't know Telugu, but, we already had this, so I just took it. If you guys are interested in some other language, feel free to find the data set and you can do the same thing. Okay, nothing stopping you. And for those who want to do Sanskrit and other stuff, you can also fine tune it over there for Sanskrit as well, right? But you will need a lot more data sets.
You used? You will tell the process of how you trained this based on the base model you used. Yeah, in this.
No, I don't know the base model how much they use, but we are fine tuning with 1,110 rows. That's it. Okay, we see this here, 1.1K. That's it.
That much, and after that it translates, huh?
Yeah, no, it already translates. So I'll show you here. In fact, I'll show you that the base model which we are taking. So we already deployed it on our GPU. This is running inference from our own GPU. Okay, so I'll show you here just for your knowledge. So we have a translate with pre-trained. So this is a pre-trained model, and then we fine tune it with 1,110 records, which I'm talking about now, and then we quantize it with 4-bit fine quantization for inference, and then we use LoRA fine tune. Okay, so this is what we are doing in sequence, and I'll talk about them. So if we translate with pre-train, right, you can actually, I'll show you here. What we can do is we can go to Hugging Face and pick up some text over here. So let's say, where are you going? Okay, so where are you going? We search, you can type anything you want. Okay, so where are you going? I go and type it over here. Where did that thing go? Okay, here. So where are you going? So this is the typical Swagger thing, right? So if you see here, it gives the output Ekkada Meeru Veltunaru, correct? So again, people who know Telugu would know that that is not correct. Okay, so it's more like where you are going. Okay, where you are going, right? That's what it's saying over here. That's not correct translation as compared to Meeru Ekkadiki Veltunaru. That means where are you going? This is the correct one. Correct? You guys agree? I mean, people who know Telugu will understand, right, and appreciate. So you see that it's not giving you, it's giving you the output. This is output. This is pre-trained. It's not, we haven't touched the model. Okay, direct inference from a pre-trained model. Correct? Now I'll ask the same question to the fine-tune model over here. This is the fine-tune model. Okay, so just sharing this so that you get an appreciation of what we are doing before you actually go ahead. So if you see what is the thing is gave? See, if you see here, it is giving where are you going means Meeru Ekkadiki Veltunaru, right? You can see the difference. This is pretty much accurate. It's exactly like what it is given here. Okay, got it. Now I know it's, I'm asking a question out of what it's trained on. Okay, I know it's like cheating the system, but what you must appreciate and understand is that it's giving the right output. Correct? That means it's working. Okay, the fine-tune process is working. Okay, so you can try out several other things. I'll maybe give this endpoint also to you guys if you want to try it out. Okay, maybe I'll put it in the chat. That's okay. Folks can try it. Okay, for those who know Telugu, you can try it out from here. Or if you don't know Telugu, you can go to this Shreya data set and you can pick up some sentences from there and ask. Okay, this is the data set. Okay, now so this is our own endpoint, guys, our own inference running on the fine-tuned model, which is running on our GPU. Okay, and all of this has been developed by the guys from my cohort program, right? I run a cohort program where I teach these guys all this, and they only develop the whole thing. Okay, so I'm super proud of these guys. We actually have a front end too, but I don't know, they're running into some problems. But it's okay. I think the Swagger endpoint is good enough. Okay, because it can help you do it. And I think this is pretty cool about Python and Fast API, right? So you don't have to break your head for Postman and all other stuff. It gives you everything within, right? And you see that it's actually giving the output as well. Look at the text; it's so beautiful, correct? So yeah. So now let's get to the core part of it. Okay. So where were we? We got this over here. We said we downloaded the data set. Okay. Now it's in a Parquet format, right? So does somebody know what is Parquet format? What is the benefit of Parquet format? Anyone?
More data and less
Compression, right? So another question I have, if you see here, they're using some HF, right? // It's not like HTTPS or HTTP or something, right? So what is the significance of HF? I mean, how do you think this is going to work? Because if you see, this is a typical data frame, correct? PD dot read Parquet is a typical pandas data frame. How would it understand?
stored in
Yeah, it is stored in Hugging Face. I know that it's coming from there. But how does a pandas data frame know it? HF is not like a universal. Is it like a universal notation? How would it understand? Because if it's HTTPS // and something in Hugging Face dash something in Parquet, it's okay. But how does it understand HF? Yeah, okay. So you guys can research it out. Okay. So again, the read underscore Parquet has some of these predefined HF because Hugging Face is famous. It has some of these common things, and they keep pulling it from there, so they enable it. Okay, so let's move on. Now, I hope all of you downloaded the data set. Now, if you see closely, it will basically saying convert the English. It is, it's again doing some pre-processing. Okay, clean the data. You're just dropping all the data right now. If you see when you run this, it is going to give you the output here. Correct? Data size after cleaning 1101 training samples. So and so, right? So initially it is 1110 samples. You can see in shared data set, correct? 1110, but after it trained it, right? How much did it get to? It got to only 1101. Okay. So out of which it does the training samples, validation samples, and you can actually see some of the sample data. Okay. If you want to check out what is the data out there. Then we are doing the pre-trained model. This is the place where we are loading the entire mBart50 model. Okay. Now this is typically 2 GB, 2.44 GB. Correct. We'll actually see it in the GPU how big it is, and because it's running in Collab and it's all in the US network, it works really fast, but it's pretty big size. So you can see this here at the bottom, model.safe tensors, 2.44 GB. That's the actual file, guys. Okay. Model.safe tensors. Now, a lot of people don't know when you say model, what is a model? You get a lot of files, correct? Here you will see sentence.bp, model, special tokens, map.json, config.json. Where exactly is the model? Model.safe tensors is the model. Okay, the actual model, which 2.44 GB, it's loading. Once it's done, means it's done. Okay, so that means your model is loaded successfully. Model size, you can see it, right? 610 million parameters. Okay, now can someone tell me what is the floating bit that is used in this particular model using this information? So now that you have the information, let me tell you what information. Now you might say, what information should I look into this, right? So the information you need to look into this is, I have a model size of 610. My bad, it's not 650. mBart50, I said, right? 610 million actually. So 610 million parameters is there, and the size is 2.44 GB. Can someone tell me what will be the floating bit? So each weight, right? Every model stores the weight, right? The weight is a representation, correct? In a 32-bit, 64-bit, what it is, correct? So 32-bit, 16-bit, and so on. So floating point representation, what is the answer? Can someone tell me? You can use ChatGPT. So let's use ChatGPT. Okay. So let's ask ChatGPT, because that's, you don't know the answers to everything. So my model has, if I'm not giving the name of the model, okay, and has a stay and the size of the model is so the beauty of ChatGPT nowadays is, it'll give you any sort of answer to any sort of questions, right? 2.44 gigabytes, correct? So I'll just put that in is 2.44 GB. Help me with the PEFT value for each weight in this model, okay? So is it 32-bit or 16-bit? Okay. So let's see what ChatGPT says. Now I'm not exposing anything. We can determine this precisely from numbers you provided. Model size converted into bytes. Blah 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 blah. And so bytes. This is giving some computation. So what is the final answer? So you can see that it's stored in 32-bit. Cool. They're not FP16. It's FP32. Okay. Now I'll tell you why I'm coming to this. Okay. What is the reason I'm asking this and why is it important? Okay. So the important reason why you need to know if it's FP32 is because when you are quantizing or when you're kind of reducing the size or the precision of each weight, you first need to know where is your initial weight. Initial precision. Okay. It's stored in 32-bit. Okay. Now some of you might be wondering, what is this, precision for FP32 and where is all this going? Correct. We'll come there. Okay. I'll come there. I'll show you an example which talks about what precision actually means. Okay. Now let's just finish this. We are pre-processing the data, so we are just doing some pre-processing stuff. Just keep running this because we don't have time to run through all of this. We have another 30 minutes. Okay. Now run the training configuration. So here we have to make a decision of how many epochs you want, what is the learning rate, and all the other stuff. Correct. And these matter with respect to how accurate you get your model, what is the resources you have, and all that stuff. Correct. So again, that's where a good AI engineer should know this stuff, right? Not running the other stuff that anybody will do. This is the core stuff that you should know what's happening, how is it happening, how do you tweak it, and all that stuff. Correct. Now the next thing is you train the model. That's the beautiful part. The final penultimate one is training the model. So you just run the single command. If you see trainer.train, done. It's getting in. How is it doing it? Because it already split it, right? Training and validation, it took 900 and 100 records and it split it and it's doing all that. Cool. Now, this will take its own sweet time. It says 20 to 30 minutes, but it'll take at least 40 minutes, 40 to 60 minutes, right? And if we train it on our NVIDIA 810G, it takes just 8 minutes, okay? On the server that which I'm going to log in now, okay? Just takes 8 minutes, boom, done, right? Super fast. And if you look at it, we are just training it in 10 epochs, and we are training it on around 1,000 records. That's it, data set. If you increase it to 10,000, it takes a hell of a lot of time, even on a GPU in the NVIDIA 810G, correct? But so then you tend to appreciate, right, what is the scale at which OpenAI and all are running, right? Imagine we are taking a small thing and the scale at which they are running is huge. Okay. Now, Atman, go ahead.
Yeah, Vijender. So if we have like a 10 times data set, does the time taken is proportional to that? Does it take 10 times time or much more than that?
You mean the data set?
Yeah. If the for fine tuning data set.
It is. Yeah. See, it's a function of the data set. See, you're saying it's more like your syllabus, right, Atman? You giving more syllabus means it's going to take more time.
I'm aligned that time will increase, but is it like a square increase? Is it directly proportional? How does it look like?
No, it's not. There's no specific function as far as I can give, right? Because it's a function of multiple things. Like it's a function of your parameters you're setting here, right? How many epochs do you want? What is the learning rate and all that other stuff, correct? Now, again, we can't really get into all these right now, right? In the interest of time, but it's not like a linear thing. Like I 10 times, it becomes 10 times. No, not necessary, correct? Yeah. So, but it definitely increases because you're trying to say, you factor in all of this stuff and get ready for that, right? Now, this will take a hell of a lot of time. Okay, so now you'll see that it's done one epoch now. It's going to take 10 epochs and going to take its own sweet time. Now, the issue with running it in the Colab notebook is that, you're not going to be waiting for say 40 minutes in front of your system now, correct? So you just go probably have a cup of coffee or come or something, or you think that it will be done and it gets. Suppose it feels that you're not active, it will disconnect, right? The GPU disconnects, and then that's it. You have to start from scratch, another 40 minutes. So it's too much of pain. So that's why it's better to run on our own GPU, okay? And of course, someone of you have actually asked it, right? Is the GPU expensive? Yeah, it is very expensive, right? So, yeah. Yeah. So GPUs are very expensive. So the GPU I'm talking about, it costs around 40 to 50,000 per month, right? And that too if I run it for just like 7 hours a day. Okay. So if I run it more is more. And a typical NVIDIA A100 or H100s, they cost 16 lakhs per month if you want to rent them out. Again from the AWS and all, but there are several other vendors in the Indian market. You can look at them separately. Okay. Now let's get back to the core point. Now we are successfully initiated the training. If some of you have already started, then this is what you should see. Just let it run. Okay, you don't have to do anything. It will run. And once it runs, you can actually run the inference over here. You can see the output. You can see this here. This is the output which has come from a previous run. Okay. So is it hello? How are you? Hello. Hello now. Right. So this is not correct if you look at it. Right. So I mean not exactly correct. So that's how it is. Now this is what it is from a typical process. Like this is a simple in mBart 610 million parameters we've taken and fine-tuned it. Okay. Now the challenge with this is that it is pretty much fine-tuning all the weights and biases within that model. Pretty much everything, right? It's doing it, but it's kind of okay for this because it's a small model, right? So if you do 2.44 GB, is not big if you look at it. 610 million parameters is not even a billion parameters, correct? Now we are looking at even Gemma, which is supposed to be like a lightweight open source model, is around 3 billion, right? Now this is nothing. Now what happens is if you really want to fine tune these kind of models, then it becomes prohibitive, correct? In terms of resources. So what people came up with is different approaches, right? And that's the topic of today, right? We are saying fine tuning, and then you have quantization and all that. So we'll get there. So before we get there, I wanted to show something about floating point, right? I think some of you might be wondering what are floating point and all. So typically, if you look at it, if I want to represent distance, okay? So let's say over here, you can see here, okay? 12 point, suppose let's say I ask what's the distance between your house and your friend's house, okay? So you say it's 12.87324923, whatever. This is a 32-bit floating point value. So that's what 32 FP means, correct? Of course, this is not exactly 32, but just give an example. Suppose it's a big representation of the distance. Now, if I were to say, hey, you know what, the distance is 12 kilometers, would it make a difference? It wouldn't, correct? What's the big difference between all these things? It's not really making a difference to me, correct? So I'm okay with a 4-bit FP value, right? Why? Because I really don't care about the small thing. But of course, if you're saying that this units is in billions of kilometers, okay, billion kilometers, if that's what is the distance that is representing 12.87 billion kilometers, then of course, even that 0.1 would be in like 100 kilometers or something, correct? So the precision is important in the context of the use case, correct? So in this use case, what I'm saying is I really don't care about 32-bit precision. Give me 4-bit, I'm good to go, correct? So if you're saying that all your data of your kilometers is stored as 100 GB in a particular file, I'll say chuck it. Just convert all of them into 4-bit values and just give me 12.5 GB, which is 1/4 of the size, right? So that's what precision is all about. And that's it. That is the central essence of quantization, correct? Quantization is basically saying the 2.44 GB model that you're taking, that whatever you saw here, right? This has 2.44 GB on it. What is that? This is 2.44 GB, right? Stored at 32-bit, 32 FP. That's what you saw in ChatGPT, right? I'm saying check it. I don't want it. Give me 4-bit, right? And I'll use that model. Okay. Now that is the concept. That's the idea behind it, right? Don't go for a big model. Go for a smaller model if I'm okay with the precision. Now, if you look at it, what is the trade-off involved? Now, in software engineering, everything is a trade-off. Now, if I'm reducing it from such a long text to this one, there's a trade-off involved in terms of precision of every weight, right? So every weight is reducing its precision. So what is the impact? The quality impact. Because you're saying earlier, a lot of effort, but Facebook to bit to give you the best accuracy, and now you're saying, no, okay, check it, I'll make it 12. You're reducing the precision it is given you, but it comes at a cost of output difference. Your difference is going to reduce in quality, but it's okay. What are we looking at? English to Telugu translation. It's okay, right? I'm okay with that. If I'm okay, I'll do it. But I'll do it only if I feel there's a need for it. If my server can handle it, then I won't do it. If my server can't handle it, but still I want to do it, then I'll do it, right? So that's what I'm talking about. So 2.44 GB is something I can handle, but what if my memory was just 1/4 of it, or 600 MB, correct? 60 MB, right? So 600 MB, right? So if I had just 600 MB, then what would I do, right? Then I would quantize it because I still want to get the job done. Now, the central essence of quantization is that. That's it. Okay. Now, I have a question for you guys. Okay. So let's say I have a mBart50 650 million parameters at 32-bit FP. Okay. Okay. 32-bit FP. That's what we have. 32 FP, which is around 100 GB. Okay. Let's say, just as an example. Now, full fine tuning is what we are doing right now, and all of them, the entire 650 million parameters is fine tuned, correct? So when you fine tune it, the model size does not increase. Okay. So because the weights are being adjusted, just the weights are being adjusted. You don't change the numbers, you don't increase, you don't decrease the parameters. They're the same. It's still 650 million parameters, just the weights are weighted at 32-bit FP. Okay. And then I do the quantization, right? To 12.5 GB, and this I am doing it for the first. So does it make sense? Is this okay? I mean, I'm now taking this model and running inference so that, I just run inference on a 12.5 GB model as compared to a 100 GB model. So inference is basically loading into memory of the server and serving it over HTTP or HTTPS, correct? So I'm doing this. Does anybody have any questions or any concerns around this approach? So I'm taking 100 GB, full fine tuning it. I got a very fine tuned model here, 100 GB, 650 million parameters. I then do quantization, which is nothing but moving from 32-bit to 4-bit. I'm reducing by 8 times. So they're becoming 12.5 GB, and I'm using this for inference. Anybody have any questions? Is this okay with all of you, or can we do something better? Anyone? Can we do something better from this? Is this design great?
So I don't know if it's better, but another option could be that you first quantize it, then fine tune it.
Correct. That's right. So that's what I'm looking at, right? So the other option would be first quantize it and then do the full fine tuning, correct? So what Atman is saying is, okay, what Atman is saying is first make it 12.5 GB, okay? So instead of full fine tuning, do the quantization first, okay? So because you're quantizing it, it's becoming now 4-bit FP, right? And because it's 4-bit FP now, then you do the full fine tuning, correct? That's what you're saying, Atman? Did I get it right?
Yeah, that's what I think. You have it already on the side.
Yeah, I have it already on the side. Oh, you
Yeah.
saw that, huh? Oh, that's why I was running very.
No, you
Atman-
scrolled it later. But
No, I'm just kidding. It's okay.
Yeah.
So, okay, I put it on the side so that you can see, yeah. So, thing is, this is the other option you can have, right? So I first quantize it, make it 12.5 GB, and then fine tune it like this. But the challenge with this is when you make it 4-bit from 32-bit, it does not have enough precision to fine tune it. Okay, so the fine tuning process requires the model weights to be of 32-bit floating point. Correct. If you make it 4-bit, it does not qualify. Okay, the precision is not sufficient enough for fine tuning it. So that's why this particular option is a no. Okay, you don't go with this. Okay, yeah. So this is what we go ahead with. Okay, now that's why you do full fine tuning and then quantization, and then to quantization to improve the inference. Okay, so that's the rationale behind it. So ultimately, you're getting the benefit of inference, right? If not for that, now now the other ideas, then people start, people keep getting ideas, right? People started getting more ideas. So people were like, okay, why should we even do the full fine tuning of entire 650 million, 610 million parameters? Because mBart50 is trained on 50 different languages. I'm interested in Telugu, and if that is the fine tuning I need to work on, why don't I just look at a specific area within this whole gamut of 650 million and just focus on those areas, right? So that's when something called parameter efficient fine tuning came up, the PEFT. Okay, so again, if you see our session poster, it has fine tuning, quantization that we have already covered. PEFT, LoRA, and QLoRA are the 3 others which we are going to cover now. Okay, so PEFT is basically parameter efficient fine tuning. LoRA is low rank adaptation, and QLoRA is quantized low rank adaptation. Okay, so very intimidating stuff when you look at it, and it will be all more intimidating if you go to any YouTube video and look at some of these guys who have no freaking clue about what they're talking. Okay, so they'll just put something by getting something from somewhere, put some something out, and they say talk something. So parameter efficient fine tuning, basically you're saying I don't want to fine tune the entire 650 million parameters. I'll just take a subset of it and fine tune them, and I'm good to go. Correct. So therefore, I'm saving on the computing cost. I'm saving on the space, both. Right. So that is just a concept. Parameter efficient fine tuning is a concept within which you have two options. One is LoRa and QLoRa. Okay. So LoRa is LoRa adaptation. QLoRa is quantized LoRa adaptation. Okay. So thank goodness it's not another different type altogether. It is just quantizing the LoRa. Okay. So we'll talk about what LoRa is. Okay. So LoRa, basically what they are saying is you take your original 16 million parameters at 32 FP, okay, right? And don't touch all the original 16 million parameters. Don't touch them, just freeze them, okay? It's analogous to, suppose you have a book, okay? You have a book, big book of encyclopedia, which consists of 1000 pages. Now you are interested in, let's say, animals. Now an encyclopedia will have capitals, countries, whatever, geographies, history, and all that stuff. But you are interested only in animals, let's say. So what do? You put sticky notes. Okay. So in the animal section, which spans from 100 page to 125 pages, you put sticky notes on the respective pages where you want to enhance the knowledge that you want to pass on to anybody else who wants to use the encyclopedia. Correct. So if somebody else wants to use it, you just pass on that encyclopedia. It has all the sticky notes. The sticky notes have the context in them. The original pages don't get touched. Correct. So that's the concept behind LoRa, right? So you are just making sure that your sticky notes have all the information you need, which you stick on top of the existing pages. That's it. It's more like RAG if you look at it, right? But the entire model has to be deployed again, right? So not the entire model, again, we'll see that also, right? It's like RAG, but you're putting it on the model at the model level, correct? You're not segregating completely. So for a long time before even I also tried out, I also thought it gets into the model and the model becomes big. But I happen to see on the server, and I'll show you shortly, that it creates a completely separate file. Okay, it creates a completely separate file with the adapters. Okay, so what does it create? It creates something called low rank adapters. It creates some matrices or adapters. So the sticky notes are nothing but the matrices or the adapters. Okay, so those are the low rank adapters that we're talking about, which are added on top of the 650 million parameters, right? So you freeze the 650 million, you don't touch them. Okay, and you add it on top of them. And when you add on top of them, you get a new fine-tuned model, which will consist of 100 GB plus some delta. Okay, so in case of LoRa, your model size will increase. Okay, in case of full fine-tuning, your model size does not increase because you're changing the weights. But in case of LoRa, your model size will increase. Okay, but it's very, very minute. And I'll show you how minute it is when I show you the server. Okay, so this is a GPU server. And I'll just show you at a high level how, what's the so then I'll come to QLoRA. Okay, let's finish up the theory first. The next thing is about QLoRa, correct? Where did the thing go? Okay, so the next thing is about QLoRa, correct? QLoRa is basically what I'm saying. First, to take the quantize it, right? Quantize it to 12.5 GB and then perform LoRa on that, right? So earlier I said don't quantize it first, right? I said here don't quantize it first, but now I'm saying quantize it. Any idea why? Anyone? Any clue? Here I'm saying quantize it first. Here I said don't quantize it first.
Because we are already freezing the original model.
Yeah, that's right. Because we're freezing the original model, right? So if you're anyhow freezing the original model, it won't matter, right? Why do you want to load in this 100 GB into memory and then fine tune the whole thing? Correct? Just take the 12.5 GB what you have and you're anyhow freezing it, add your adapters on top of it and perform LoRa and you get something out. That's it. Cool. So that's the idea behind it, right? See, again, that's engineering, right? See, and you can only do engineering if you understand the stuff behind it, what happens under the hood, correct? So here what we are saying is LoRa, we are saying just freeze the base layers and just add LoRa adaptations or matrices on top of it, like the sticky notes, which are going to give me the enhancements. And QLoRa saying, okay, let me just quantize it first anyhow and again freeze it and then add the LoRa adaptations or matrices. That's it. Cool. So that's what we're talking about. So again, if you look at the math behind it, it introduces an R matrix. Okay? So if you know matrix multiplication, I think Himanshu asked the question, do you need math? Yes, you need that math to understand how it works, right? So you have A into B. You generally, if your original matrix is A into B, you say R into A, and then you say R into A, and so A into R multiplied by R into B, correct? That's how you split it, right? Again, some of you guys are maybe, I mean, I'm not so great at math, but if you have a matrix of A x B, how do you split it as, right? Matrix multiplication says A x R, if you multiplied by RXD, right? If I'm not mistaken, this will give you AXB, correct? A by B, correct? So what the concept of LoRa does is it introduces that R in between, which is a very, very minute set of minute number of rows that actually does this whole thing, and those are those adapters that get in, or the matrices that get in. Okay. Now again, I won't get into the math behind it. It's huge, but if you're interested, you should get in and literally get it and get to it. And that's when you come up with new ideas, correct? How do you come up with a better way, right? So that's the thing. So guys, clear on the theory? PEFT. So let's do some quick recap. Okay, quick recap. We are saying original model had 32-bit FP, 12 point this thing. It was a total thing. We said 12 kilometers. We said 32-bit to 4-bit FP is reducing the size 1/8. Just flat, guys. It's just 1/8. That's it. That's as simple as that. And I'll show you in the GPU how the size looks like. And you have to see it to believe it. Okay. Sometimes, you know, people state a lot of all sorts of stuff, but you have to see it to believe it always, and that's the fun part of it, because that's what matters when you're doing inference, because you're loading it in memory. Okay. Now, next thing what we said is in full fine-tuning, what we are doing in Google Colab is full fine-tuning. We're taking all 650 million and fine-tuning it, too much of time, too much of memory. So we are saying, why don't we just quantize it by taking the fine-tuned model and then reducing the size for improving inference. Okay. But we're taking the central idea of quantization and doing the inference. So then we said you cannot quantize first and then fine tune, because the precision of the weights is not sufficient for a fine tuning. Then we said let's use PEFT, okay, for parametric efficient fine tuning. So we said don't fine tune the whole model. Let's take a subset. So LoRa said, you know what, freeze the base model, just add your adapters and matrices on top of it and train them and get it out. And QLoRa said just quantize it first and then do LoRa. That's it. Cool. So this is what it is. Now, any questions here so far before we move on? Okay, great. So now I'm on the GPU server, right? Okay, so NVIDIA, what is the command for that? Have been SMI. Okay, great. It's working, right? So that means this is a GPU, right? So here you can see this is a GPU running CUDA version 12.2. This is an NVIDIA 810G. You can see it here, right? If you want the specs for that, you can research online. Now the point is, so if I now let's just go to the you know, home Ubuntu GPU, and here you can see these are all the folders. And these are all the guys in my cohort, guys. You know, again, some of them, not everybody is actually doing this because some of them have other interests. So these people are, you know, again, Dr. Prasad has just, okay, I need to be sudo. Okay, home Ubuntu GPU. Okay. So if you see this English to Telugu mBart50 is there, right? So -al du-sh star. So if you see the size of this, right? If you look at the size of this, this folder, this English to Telugu mBart folder, you see how much time it's taking. It's 45 GB. Okay. So if I look at it, what is there inside? So of course, this 45 GB is, again, I'll do du-sh star. I'll explain what's going on here. Don't worry. So if you see this whole folder, English to Telugu mBart, this whole folder has all the code that we used for fine-tuning this. Okay. So if you want, I'll also give you my repo. So we have this Alumnix AI Labs. Where is that? Yeah, let me see. So this repo is on our Alumnix AI Labs repo, English to Telugu mBart. I'll give this also to those who are interested. You can check it out on your own as well. So this is what we use to deploy. Okay. So now you can see here, you can see that I'm printing out the size of each folder within this, and you can see the size of the virtual environment here is 7.3 GB, correct? So this includes your entire torch and everything. Just the VNV file is 7.3 GB, and you can see the size of the fine-tune model. Okay, where is the fine-tune model in this? No, it's not here. Oh yeah, it's here. It's here. So you can see 2.3 G. That is the folder. Okay, CD mBart. Okay, ls space -al. Okay, so du space -sh star. So you can see that model.save tensors, right? This is the core model. If you see in the collab also, you'll find the same name, model.save tensors. So this is the actual model 2.3 GB that's there on the disk, right? Now, this is the original, this is the fine-tuned model. Okay, and if you see, where is the, does somebody know where the original model will be? Has anyone tried this before? If you pull it from Hugging Face, where does it go? Any clue? Where is that? This is the fine-tuned model, right? What I showed you is 3.3G is fine-tuned model over here. It's model is same. This is fine tuned. Where is the pre-trained model? Does anybody know? So it gets into something called the dot cache. You can see here dot cache. So it gets into dot cache, and you can be able to actually see it. You can go to Hugging Face, and you can go to Hub, and you can go to models. Okay, and within that you go to blobs. Okay, so du-sh star. You can see that the file is over here. This is the original model which came from Hugging Face, 2.3 gigabytes. That is downloaded from Hugging Face. So imagine the amount of data that Hugging Face serves. Okay, this is the model we've taken, and we've run inference. Now the link which I shared with all of you over here, this is the link which is powering the inference which is coming from the pre-trained model. This is the pre-trained model, guys. Okay, so this is the pre-trained model. I've shared this link in the chat. Okay, I'll share it again if you want. Again, you guys, when you're running inference, it's running from our server, proudly powered by our servers. Okay, so this all has been developed by Vishal. I don't know if he's in the call. Yeah, Vishal is in the call. Okay, so Vishal, I'll just need your help on the LoRA part of it. Okay, so because that even I haven't done, guys, because the first time even I have done the LoRA part of it. But let's still do it. So again, we won't go beyond 12:30. Don't worry. Okay, I know it's been a long time. So if you look at it, 2.3 GB is the size of the model. Okay, now I'll show you the size of the quantized model. Once you quantize it, what will be, right? So CD mBart fine-tuned model, we quantize it, correct? So du-sh. Okay, so if you see it, the size of the quantized model.safe tensors is 668 million MB, sorry, 658 MB. That is 1/4, right? Is it 1/8? 6 4s are 20. It should be 1/8, right? Actually, 2.4, 2,440. Yeah, 2,440 divided by 8 should be 300. No, I think this is Vishal. What is the quantization used here? Is it 16 or it's 1/4? Yeah, 1/4 of 32-bit is 8, right? 8-bit. Yeah. So if it's 668 MB, correct? So, but anyway, let's look at the fact that it got reduced. Okay. Now, because I don't know who created this and I don't remember the configuration. So, but the idea is once you quantize it, you're loading only 68 memory MB to memory and running inference. Now, let's look at the LoRA, right? What we did in LoRa. LoRa, what did we do? We froze the base and then we added some additional layers, correct? So I go into mBart. Okay, where is that thing? Where is that LoRa? Yeah, mBart hyphen LoRa fine-tune model. Okay, so here if you look at it, okay, it's just 17 MB, guys. Okay, if you look at it, it's just 17 MB. So these are the adapter underscore model of safe. So that is what is introduced newly. Okay, so that's why they say that even if you put in a LoRa on top of it, like you're adding additional adapters on top of it, that's the additional impact you're talking about, and that's why they say it's minimal. Does it increase? Technically, yes, but if you look at it from a weights perspective, it's very insignificant as compared to 2.4 GB. Correct? Now, what QLoRA does is it just reduces the original to much lesser and then introduces the same 17 MB. Okay. So, Vishal, do you want to explain how you have enabled the inference for this? Because model.safe tensors is the original model and 17 MB is the adapter model. How did you kind of piece them together? You want to talk about that?
Sir, actually, I'm right now outside. I might not be able to continue.
Okay, fine. Okay, no worries. Okay, so but again, so Vishal is the guy who is he's in our cohort member, and I said, "Are you up for it? Do you want to run inference?" And then he put up all of this stuff, and he himself did all this. Okay, so that's pretty cool stuff. But the idea is it sets a foundation to understand and appreciate and get a mental feel of what is the size of what we're looking at. Okay, so now maybe if you look at Vim tokenizer.json. Okay, so if you see here, what does it contain? Can you see this? It has the content and the token IDs, guys. These are all the tokens that come from it. Okay. Can you see this? This is all the tokenizer that's attached to this. So how does it get the output final value for a given token? The model predicts the token, it gets a name from the token ID. So this is how it gets it. So this tokenizer is important for it to function, correct? This is what it is, 17 MB of tokenizer. Okay, that's necessary, right? And again, that comes from where you kind of train it and put it in. Okay, but again, there's a lot of stuff, you know, you can't cover everything in one session, right? But pretty much at a high level, this is what it is, guys, with respect to fine tuning. Okay. And I shared this also with you. You can try it out on your own. So let's try again. See, I mean, since we have 4 minutes, let's just try some sentences which are like where the base model really doesn't work. Vishal, do you have any sentences like that? Where the base model really does not perform great, but the pre-trained model does.
Yeah,
Or Lakshman,
one of the
Yeah, I have
sentence.
few sentences, but I didn't actually try it on inference. We can try it live, I guess. I have few sentences.
Okay, so tell you, I think this guy's tried out some. Yeah, so add to cart and apply the coupon code at checkout. Okay, so if you try this is what happens in the base model. So let's try it out. Okay, because ultimately that's the proof of the pudding, right? Translate with pre-trained. Okay, so you folks also can try it out, guys. Okay, so you can click on try it out and click on it and enter this. Okay, so again, it will run as long as the GPU is running, guys. Okay, so we'll not keep the GPU on the whole day. So if you can see here, you can see Urdu over here. Sorry.
Can you give me the link where I can try the inference?
What is the question?
Can you give me the link where I can try the inference?
No, it's okay, Lakshman. Just wait. Okay, so so guys, if you look at it, add to cart and apply the coupon code at checkout. If you see here, you can see some Urdu text, correct, or whatever language that is. So if you try this, because it gets confused, the pre-trained model gets confused, correct? Now we are saying let's try it on a fine-tuned model. Okay, so I hope it better work here. You know, it's exam time, right, Atman? Exam mein hi padta hai. Let's see. I hope it works. So if you see it here, it's not broken, correct? Can you see this? Cardlo చేరండి మరియు తనిఖీ వద్ద తప్పు కోడ్ ఉపయోగించండి, right? If you look at it, again, for those who know Telugu, it's pretty good. No misses, if you can see it, right? So here, if you saw, and you saw, మరి తనిఖీ వద్ద, you see this coupon code. So prayogistaru. It's not even correct, right? If you look at it, but the fine-tuned one is pretty good, right? Now let's try with the same thing with quantized output. Is it affecting the output? Yeah. So let's run this.
What my research shows that it mostly fails on the modern languages or modern slangs.
Sorry, your voice is breaking here. Who's that? Can you come again? Is someone saying something?
So this pre-trained model mostly fails on the modern terms.
Okay, that's fine, Vishal. Yeah. On the model run, sir. Okay,
No,
I can't hear you.
modern
That's okay.
English slang words. He's saying it doesn't work for modern English slang words or the usual colloquial phrases
like
that
cart, checkout, cart, probably those.
Correct. You got it. So that's okay. See, I'm not too worried about those, right? So I'm looking at the Telugu part of it, right? Even if you look at this, now the quantized model is not performing very well, if you look at it, right? Saying carp low cherandi mariyu thaniki the kapu code no private. It's coming okay, but it's not so this thing. Now let's look at the LoRA fine tune, okay? And let's check out. So add to cart and cart చేరు మరియు దానికి వద్ద టోకెన్ ప్రయోగిస్తారు. Okay, so it's giving some output, but again we have to check the quality of it in more detail. Okay, so but again this is a high level idea, guys. Okay, you get the idea, that's good enough. You can try it in the data set and try it out yourself. So that's the thing, folks. Okay, so tomorrow again I'll have the same session, and I'll have a quiz also tomorrow. I thought of having today, no time, and I'll give some GPU hours tomorrow for those who perform well on the Kahoot quiz. Okay, so people who join my cohort, right? So again, just FYI, I'll do some promotion of myself. Okay, so I run this firm, alumnex.com, right? So this is the program I have. So this is there's a new program that I have anyways. So yeah, this is the program I run, and I give GPU access to the guys who join my program, and we do a lot of we cover a lot of these programs as well. So you can check out. I think this page is not updated. Courses, I think new course. Yeah. So this is the page. Okay, I'll just put it out here. If you guys are interested, you can reach out to me, and you can just enroll for the free trial, right? And I'll tell you how it works. So one unique thing about this program is it's powered by an agentic AI application built by me called Study Buddy. Okay, so typical edtech firms, what they do is you join a program and then you lose interest after a week, correct? And that's what I started seeing even in my program. And people join, within a lot of Josh, I want to do this, that, and all. But then after 1 week, 2 weeks, they're gone, right? And then it's hard for me to chase them, follow up. So we built something called Study Buddy, and I'll update the details on this page too. It is an agentic AI application which will monitor your progress and make sure that you are studying at every time, right? And you can enroll. I just join the free trial. I'll explain to you how it works. And we have something called Project School where we assign the projects. So it's projects based. We assign the tasks and you keep completing the tasks, and agent keeps monitoring it. Correct? You see Study Buddy on the right. The agent keeps monitoring you and checking are you doing or not doing, and it sends you a mail daily. It sends me also reports. Correct? So let's say Atman signed up with full Josh and he says he wants to do his tasks. 1 week is over, nothing is happening. He'll get a mail. I'll also get a mail. So I'll call up Atman. Okay, I'm not leaving him. So that's how it is. So we pick up the task and do it. And this is a revolutionary program from an invention from me. Simply because I feel it has to add value. We've been solving problems along the way, and I thought this is the best way out. Okay, so again, you can check out my program page if you're interested. You can sign up for the free trial, and I can just help you understand if it makes sense for you or not. Okay, the goal is we build projects from scratch up, less like you're doing. This entire stuff has been developed all by our core members only. I just teach theory. These guys build it, and if they're ready, I give referrals for companies. Okay. So Vishal is the guy who built all this, and I'm already referring him to a couple of startups, right? And I'm sure they will take him. He'll get placed. I'm sure about that. I can say with confidence because he's ready. He's done all this stuff, most of it without me telling him also, right? So it's just giving the platform to do the real stuff, get the experience, and taking things to the next level. Okay. So that's it, folks. Thanks everyone for joining. And any questions, I'm happy to take. Yeah, if you have any questions, happy to take, or if you have any general chit chat you want to talk, we can do some general chit chat for some time. Yeah.